chapter 2, we're going to actually start looking into what factors influence organic chemical reactions. And we'll do a little bit of review, okay, on geometry using primarily the VSEPR model. That works just fine for organic chemistry. We don't have to go molecular orbitals. If we did, I'd be in trouble. Okay.
Did we learn about that in Chem 2?
Yep.
Orbitals?
Molecular orbitals actually at the end of first semester.
Yeah.
Mm-hmm.
I actually like that.
We did the bonding.
Yeah, I like that.
Yeah. It made sense.
It actually did.
Yeah. So there are a whole host of concepts in chemistry that don't make sense.
Yeah, literally, and that one actually did.
And when
That would say it.
we get to that point, I go back to my fallback position. Nature just does what it does, and we're trying to explain it. And science is ever changing, right? Anybody says to you the phrase settled science, you can do what you want. Laugh in their face, spit in their face, call them a liar. There's no such thing as settled science. Okay. In order to, this is going to be kind of a, since we're only dealing with, in organic chemistry, primarily carbons and hydrogens, and then some oxygens and sulfurs, maybe some halogens. What we want to do is identify a quicker way to set up a three-dimensional model, right? And as you practice it, it becomes kind of second nature. You'll say, all right, if I have this structure, if I have this formula, then I can have this structure or that one based upon the model. Okay, so the first thing we want to do is remind you that when we, in the VSEPR model, if a carbon is bound to one pair of electrons, or two, or three, that's all considered one group. Right? So when we assess the three-dimensional structure, if we had something like this and this, and that, and maybe 1, 2, 3, 4, let's see, they're too close together. If we did this, that's obviously 4 groups. So we have a tetrahedral structure arrangement around that carbon. If we have, and carbons, typically, unless we're trying to form some sort of an ion, they typically have 4 bonds, right? So that's the first trick. We talked about that one last week, I think. So this one only has 3 groups. So this one would be tetrahedral. This one would be trigonal planar. And this one would be linear. Okay. Around a carbon. Well, we'll get there. I'm starting to step on my own toes. Okay, just a reminder. When we're drawing the structure, trying to find the molecular geometry, you got to go through the electronic geometry first. Best example of that is ammonia, right? If we did ammonia, the VSEPR, we would have a lone pair up here. We would have one in the back. We'd have one up here and one out here. So we have this kind of a trigonal base and this pair up here. So what we're looking at electronically is a tetrahedron. But we want the molecular structure, and that's a trigonal pyramid. Okay, so you go through the electronic geometry first, then you get the molecular geometry. Now, we don't forget about that lone pair, because when we start talking about chemical reactions, lone pairs are very important, right? And we'll get into that a little bit more detail when we talk about curved arrow notation. Okay. We already talked about that. Well, the bond angles, of course, trigonal planar is 120-degree bond angle. tetrahedral nominally is 109.5 degree bond angle. And linear, of course, is 180 degrees. That hasn't changed.
So we're having a lab after we do chapter 2, right?
Uh-huh.
Sorry to get off topic.
Yeah.
So we don't, or do we need a lab notebook for this? Like,
No. Uh-uh.
So no lab notebook like, nothing like that? Okay.
No. That's too much effort and too little time.
And so the lab actually goes towards our overall grade, right? Like it's
Yeah, uh-huh.
Okay.
Yeah, that's
You probably went over that. I was working
okay.
Wednesday.
Well, it's in
I
the
was
syllabus.
listening, but, okay.
Yeah, the grading scheme is in the syllabus. Yeah.
Sorry to go off topic.
Um, we already talked about that.
So
Yeah, that's okay. We can get back in gear. Okay. And this is a basic concept of ESEPR. What we're trying to do is put the electrons, bonded and lone pairs, as far away from each other as possible because of the same charge. So that's why this one is going to be 180 degrees. That's the farthest you can get away these electrons on either side. We have to squeeze them a little closer to get 3 in there and even closer to get 4 in there. So that's why the bond angle decreases from here to here. If your central atom has a lone pair, that does affect the geometry. And it does it in this form right here. You fit the electrons as a group into the geometry, and then you go from there to find the molecular geometry. Let's see. Now, if we have an ion, here we have 2 possibilities. If, say, methane, say we start with methane. And for some reason, this hydrogen is transferred to some other molecule. Remember, hydrogens don't exist as single protons floating around. They're always transferred from something to something. If this hydrogen goes somewhere else and it takes those electrons with it, then we end up with a carbocation, right? And we can justify this by doing the formal charges on these guys, right? If we do a formal charge on carbon, it starts off with 4 valence electrons, right? 4 electrons. How many does it have? Well, it's got 1 from here, 2, 3, minus 3 equals plus 1. So that's how you get the charge. If, on the other hand, that hydrogen leaves and the electrons stay behind, right? So we just transfer the proton. Then you get this possibility. And this is a carbanion. Let's see, this will be negative charge. So the geometry of this one is simple. It's a trigonal planar, right? And that has an impact on how on its geometry as a result of a reaction, or its attack. Something is attacking it. It can actually trigonal planar with a positive charge. It can come in from this side or that side. Either way, we'll get to that later, hopefully. But with a carbanion, you still have a tetrahedral electronic structure. And that means that you're going to have a trigonal pyramid with a lone pair up there, just like ammonia. And if you've got something coming in that likes electrons, we call those electrophilics, they will come in and they will attack the side with the lone pair. So that will have an impact on the geometry. Right? You could have a mixture of either isomer, and we haven't talked about those yet. But in this one, the largest share of the products will have only one, have a dominant one isomer because it only comes in from one side. I'm trying to make this relevant. Okay, so how do we represent these things in three-dimensional space? There are a host of different ways to represent a three-dimensional structure on a two-dimensional plane. Right. When we drew the line structures in the quiz, we're really not saying anything about their three-dimensional structure. We can't, not that way. So this is one way that we do it, the dash wedge notation. So let me keep track of what we're talking about up here. Because there are several different notations that are available to us. So the first one we're going to talk about is dash wedge. Okay. If an atom bonded to any other atom, but in this case, we'll keep it simple, carbon, is bonded in the plane, then we use a line. Right? So if this carbon is bonded to this hydrogen, they're both in the same plane. Okay. And say we got another one here. They're both in the same plane. Well, we know that if methane, and that's where I'm headed, methane, if methane is tetrahedral, that means the other two can't be in that plane. So if we want one of them coming out of the board, then we use a wedge. And if we're going into the board on the other side, then we use a dash. Okay, that's the dash wedge notation. And if you kind of have to visualize it, maybe if you use a model, maybe this is a good place to pull out the models. Okay, blacks are always carbons, and the carbons come in two types. They have 4 possible bonds on them. Some of them will only have 3. If you've got a carbon in a trigonal planar molecule, then you want to use the one with only 3. But I can't find you in this one. These are all 4. Now here's a 3. Set that one aside. This one, that's a 3. There's a 4. Okay. Carbons are black, hydrogens are white. And I've already got some of them. They were left connected, so that makes it simpler for anything. As an instructor, I probably need larger models so you can see them from the back of the room. But if we lay this down, if we say like this, where these hydrogens are in the same plane, like that, then you can see where this hydrogen comes out of the board and that one goes into the board. Okay. That's dash wedge. Now, we can also, and I see they've done that, they rotated them around. So if you rotate it around so that it sits like this in that other model, now you've got nothing in the plane of carbon. You got these 2 wedges and these 2 dash. But it's the same molecule. It's just oriented differently. That's another peculiarity about three-dimensional organic chemistry that'll come back to bite you very, very often, is recognizing what structures are the same and what are different, because they can they can occupy space differently, but it's the same molecule. So that's why I think that this is going to sound sexist, but it's been my experience that women do better with the geometric part of organic chemistry, because you guys think in 3 dimensions more so than men do. We're usually stuck on the left side of our brain, and sometimes we use the right side, but they don't talk to each other very well, except for one group of people, musicians. If you're a musician and you start training before puberty at a young age, then that corpus callosum, connection between the two hemispheres, is much, much stronger. Okay, so back to the topic. Let's see. This particular model, butane-2-ol. Now we haven't talked about how to name the alcohols. Right? But take my word for it. We're still starting with the longest chain. In this case, the longest carbon chain is 4 carbons long. And then if it's an alcohol, we're going to put an OL on the end instead of the ANE. It's not an alkane anymore. It's an alcohol. So we put the OL on the end, but we squeeze in where that OL is located. Right? And it's on the carbon, second carbon. That's what butane-2-ol means. We used to, a long time ago, we used to say 2-butanol. But I think that somebody decided that was confusing. So we switched. Okay, so you can look at each one of these carbons in terms of its three-dimensional structure. And you can draw a dash wedge for each one. And then, but one of those connections is going to be to another carbon rather than a hydrogen. And then from that carbon, you also get another dash wedge. And remember, and here's another thing about this three-dimensional merry-go-round is single bonds can spin. You can spin around that single bond, no problem. So this is one way to look at it, but we could take that number 1 and number 2 carbon and spin everything on the number 2 around the other side. Now, the only thing that would possibly prevent it from spending most of its time there is steric interference. If you got big parts of the molecule and they get in the way of other parts, then it would be more likely, even though it's spinning, it would spend most of its time in one position. Right? And there's another way of representing that to take advantage of that possibility. And that will go up here with the others once we get there. Okay. So here we can flip this molecule 180 degrees top to bottom. Right? So you would draw a plane right here and just flip it around that plane and see what you got afterwards. Right? If we drew, it'll take a while to build that molecule. So let's go with the pictures. So that's the way it looks. And now we're going to go here and say, this is the way the model would look, right? The OH, of course, the hydroxyl is coming out. That chlorine, which is green in our model, is coming out. Oxygens are red, chlorines, halogens are green. And we've got another green out the back, okay, because it's got the dashes on it. Okay, so what happens if we rotate that one around that plane? I mean, around that axis. Okay, rotate that one around the axis, and you get, now you get the apex, so to speak, on the bottom. And since the chlorine was in the back, as we rotate it around, now it's in the front. Okay. So what happened to the other ones? Well, let's see. The other chlorine, second chlorine, is out. So when we rotate that one around, it goes back.
So dash changes to the wedge, and the wedge is changed to dashes.
Yeah, in this case. I don't want to say every time
Right.
because it depends on the axis that's rotating. And if this were a more complicated molecule, say you had, instead of OH down there, you had some alkane attached to it, then that can also be flipping around. So it can get complicated really quick. We're trying to keep it simple at the beginning. So on the simplest basis, I think you're right. And it depends on the axis that's being rotated too. If we rotate it right here, say we rotate it there, this one would probably stay the same. It depends on the axis of rotation.
Flipped it 180 degrees.
Yeah, if
And
you
where
if you flipped it around, let me think of this. If we had a vertical axis and we flipped it, no, that chlorine would come out in front. Yeah, it would. Because the axis doesn't go through the chlorine, it goes between the chlorine and the hydrogen that's not drawn. If there's where a line ends or two lines meet, there's a carbon, always. And then since carbon has 4 bonds, any bonds that are missing, we fill them with hydrogens. That way we don't have to write everything in the world in there. Okay, so this would take some, I would say it takes some practice building models and flipping around. If you have any questions, just go to your models. Okay. Dipoles. Dipoles, we talked about this last time, I think, in the chapter 1. But just as a reminder, you need to know 2 things to determine whether a molecule has a dipole. The overall dipole for the molecule. You have to know, you have to have polar bonds, and you have to have an unbalanced geometry. Say if you have carbon dioxide there, you've got dipoles toward the oxygens, but they're equal and opposite. So overall, the molecule has a net 0 dipole. Excuse me. But as far as reactivity goes, you still have that accumulation of electron density out there on the oxygen on either side. And we didn't draw in the lone pairs. There are 2 lone pairs on each one of those oxygens. Oxygens tend to form, let's just do that. Let's see, carbons, 4 bonds. And lone pairs, typically none. Oxygens, 2 bonds and 2 lone pairs. This is under most circumstances. Nitrogens, 3 bonds and 1 lone pair. And halogens, fluorine, chlorine, bromine, they form 1 bond and no lone pair, and 3 lone pairs. I was about to rob them of their octet. Let's see. Sulfur would be like oxygen. It's similar, it's in the same group, so it would behave like oxygen. Phosphorus would behave like nitrogen. Silicon would behave like carbon. In case we ever run into those. Water has, let's see, hydrogen fluoride has a very, very polar bond. And that 1 bond is equal in polarity to the entire molecule of water. So remember, I think we talked about this. Like dissolves like, or did I talk about that in my other class? Gets foggy. But it's true, whichever class. Like dissolves like. Polar dissolves polar, and non-polar dissolves non-polar. Yeah, it was in the other class. All right. So this is a reminder for you guys. Okay. Tetrachloromethane, right? It has polar bonds toward the chlorine, but the net polarity of the molecule is 0 because they're symmetrically arranged around that carbon, equal strength of the polarities, and they're positioned in such a way that they cancel each other out. Dichloromethane is a little bit different because you have hydrogens that are less polar than carbon, so they tend to be polar toward the carbon, and then the chlorines take even more of that polarity toward their side of the molecule. So this dichloromethane is even more polar than water. we should be able to dissolve dichloromethane in water. Chloromethane is actually even more polar. That's odd. Slightly more polar. I don't know if I would have predicted that one. Okay. So what happens is this polarity, molecular polarity, has an impact on two things: physical properties and on chemical properties. We're going to talk about physical properties right now. So if you have a compound that is the salt of a carboxylic acid, did I tell you about the carboxylic acids? If they have this one, and on the end of the molecule, you have that and that. You have a carbonyl and you have a alcohol together on that carbon. That's a carboxylic acid. And it's relatively acidic because it can donate that hydrogen to a water molecule in solution. Think of acetic acid. It would have a methyl group out here. That's acetic acid. And when we did our titration to determine the Ka of acetic acid, we found that when we started out, this pH, we started out down here at about, I don't know, 3.7 or 8, something like that, before it finally reached its buffer zone, and then it leveled off until we neutralized everything, and then like that. So we were looking for this place to find our pKa. Remember that? Okay. But it starts off in the 3s. So it's fairly acidic because of that hydrogen and that functional group. Like, yeah, we did talk about functional groups last time. I remember now. Okay, so what impact does that have on boiling point and melting point? It increases the boiling point and melting point. Because of that acidity. If you can get the more strongly polar molecule to interact with one another, you increase the boiling points and the melting points, right? You get that stronger intermolecular attraction among the molecules, increases the boiling point and melting points. One thing that we used to do when we were trying to analyze a sample for fatty acids. Right? So fatty acid is going to have actually several. Let's see. Well, we start off with a true fat. We bond this acid. We form an ester with the acids and glycerol, but we hydrolyze it, and then we get our fatty acids. So we got our fatty acids have this group plus some long aliphatic chain, right? And all natural fatty acids have multiples of 2, even number carbons. But we get a mixture of these off of our true fats, and we want to know what's the nutritional quality of the forage, say, that we were analyzing. So we want to find out what's the analysis for each one of these fatty acids. And we wanted to use gas chromatography to separate them. Well, these guys are not volatile enough for gas chromatography. Their boiling point is way too high, right? So what we would do is once we hydrolyze the fats, then we would methylate them, right? Take away that acid part. That would decrease their boiling point. We'd still have this polarity in here, but now we wouldn't be able to make an acid out of it. So that's an ester, a methyl ester. And forming that ester decreases the boiling point. Now we can pump them through the GC and analyze the samples. Okay, ethanol it does have that polar hydroxyl on it. That bottom one has the ability to hydrogen bond. Right? Anytime you have an OH group or NH group, well, OH, NH2, or a halogen and a hydrogen, which are not as important for a whole molecule because they can only form one bond. So you've either got HCl, HF, HBr, but for an organic molecule, it's usually oxygen or nitrogen that allows you to hydrogen bond. So what we see here with ethanol is that we've got that ability to hydrogen bond with that OH. And if the carbon chain is short, then you get an increased boiling point. If we make the chain longer, then you have less probability of that OH hydrogen bonding with some other OH group. So that steadily decreases the boiling point. So methanol, see, this is called a homologous series, where you have, right, that's methanol, and then you have C2H, let's see, C3, CH2OH, that's ethanol, and then you can have propanol, and on down, butanol, pentanol, so forth. As you increase the chain length here, you decrease the ability to hydrogen bond because these guys are getting in the way. So the boiling point decreases, BP decreases as you increase its chain length. Yeah, there it is. All right, I spent too much time on that slide. Let's go. So the functional groups have an impact on the physical properties of our molecules based primarily on their polar nature. The more polar the bonds, the more likely you are to increase boiling points, the melting points. The more polar, the more soluble in water. Right, so that column over there says solubility in water. And if you look it up in a reference manual, it's usually given in this form. How much in grams will go into 100 grams of water? So you have 100 grams of water, and this says this is how much by mass of this compound will be dissolved in that at saturation, at temperature, usually at 25 degrees Celsius. And it's given that way because it's the most practical way. It's not the way that you wouldn't use that value for stoichiometry because the total volume may change depending on what you dissolve in it. Right? So you want to know how much is in a given volume, then you go to molarity. But once you know how much you put into the 100 mils, then you can calculate the molarity. Dipoles, we're given dipoles for the molecules. That one's pretty high. Ethanol, acetaldehyde. And these names, they bear, you may notice this as we go, they bear a resemblance to one another's. This acetate or acetic acid, CH, there. That's acetic acid. Acetaldehyde simply takes and turns it into a hydrogen. Yeah, turns it into a hydrogen. So we have this carbonyl group on the end, and that should reduce its polarity because we've removed that one oxygen. This is still, this hydrogen can still behave as an acidic hydrogen, but it's not as readily given up. Methoxymethane, that's the proper name, methoxymethane. Dimethyl ether, you'll still see that on the can, right? By the way, if you've got any old cans of ether, either methyl ether or diethyl ether in storage, before you start manhandling it, check around the, especially if it's ever been opened, check around the lid where the cap is, and if you see white crystals there, don't touch it. Those things are very sensitive and can explode. And then you call hazmat. You guys have a hazmat team at the hospital? You should.
Who it is, but I'd say we do.
You got a number to call?
Yeah.
Okay. Okay. I don't think we've gotten to how to name double bonded and triple bonded. I mentioned the single bonds for aliphatics ends with A and E, double bonds end with E and E, and triple bonds end with Y and E. So that's why this propene has a that ending, because it has a double bonded carbon in it, and compared to propane. So what's the difference there? There's not much difference between those two in their boiling point, melting point. We haven't changed their polarity that much. Now the double bonded carbons, they're slightly, well, I better not go there. Let's move on for now. I will add this. Well, remind you of this. If you have the ability, if the molecule is polar, then the most dominant attractive forces, the intermolecular forces, are dipole-dipole interactions. Okay. If you have no dipoles there, then the London dispersion forces take over. They call them induced dipoles because they only last for a split second. But they're what we studied as London dispersion forces. Now, those are always there. London dispersions never go away. But if you have a dipole in your molecule, the Londons are like several orders of magnitude weaker, so they don't matter. Okay. So this is just a reminder of our possible interactions, and we've talked about those. You can have ions interacting. You can have ions and dipoles interacting. That's missing. Oh, that's the last one. Excuse me, the last one. You can have hydrogen bonding, which is a special case of dipole-dipole, which is the strongest dipole-dipole interaction, hydrogen bonding. Then you can have your London dispersion forces. And as a general rule, the greater the concentration of charge that are involved in the intermolecular interaction, the stronger is the attraction. So, and when we say...
Are you muted for your recording?
No, it's good. It's picking up my voice. I think what I've muted is these speakers,
Oh, okay.
so we don't get feedback.
Gotcha.
It's good you caught that.
I just didn't want you to have to redo all this again.
No, I wouldn't. I've got a previous recording that you can watch. But it's from the Greenbrier campus, so it'll look a little different. Okay. So when we say the greater the concentration of charge. The one error that we could make is to say, all right, we're talking about a complete charge, so we've got to have a plus or a minus at least. Right? No, when we say concentration of charge, we mean even partial charges are valid. Okay? We can have partial charges. But we still want to say, what is the possible, how is the charge distributed in the molecule? Is it concentrated on one side? Or is it distributed throughout the molecule or over several atoms? That would make it more diffuse. That would decrease the attractive forces. Okay. This just illustrates something we've already seen before. Intermolecular forces that are responsible for phases, right? And the intermolecular forces that are available to the molecules are the same, no matter what the temperature is. It doesn't matter. What the temperature does is either, if we go high enough, overcomes those attractions, or if we go low enough, allows those attractions to express themselves. So if we decrease the temperature of water, go to the left, now those attractive forces can hold them in this crystal structure. Or if we add heat to the water molecules, now we're overcoming any attractions whatsoever. And now all these water molecules in steam are just, they're free agents. They could care less if there's anybody in their neighborhood. Okay. Ion-ion interactions are significant in organic chemistry. And if we want a strong charge as, say, an attractor for either a positive or a negative, even slight positive, slight negative, then we can use ions to do it. If we combine formic acid, right? This is your carboxylic acid, right? Whatever we put over here changes the name, of course. If we have a hydrogen over here, that's formic acid. Actually, that's the trivial name. The standard, the IUPAC name is methanoic acid. And the oic acid is the part that identifies this. So if we had acetic acid, what would we call that one? Instead of acetic, we'd say, right, this is ethane, ethanoic acid. And if you ever get a look at foreign publications, everywhere else in the world, they call it ethanoic acid. Well, if they publish in English. In this country, we might say acetic acid. Or if we had CH3, CH2, COOH, that would be propane. So that would be propanoic acid. Okay. Now, if we replace that hydrogen with a cation of some kind, then we have this ionic compound. And that makes this one a fully charged oxygen. It's very negative. And this sodium, usually, in cases like this, that sodium is a spectator. The interesting reaction is going to take place here. Okay, dipole-dipole interactions. You can still get, even with a, now this one does have a net dipole. because let's see, that's dimethyl ether or methoxymethane. It still has a partial dipole, simply because that oxygen is a more electronegative than the carbons, and it draws electron density to itself. So overall, this one is slightly polar, although it's not very polar. In fact, it may be so low in polarity we classify it as nonpolar. Okay, which compound has a higher melting point? The ethanoic acid or acetic acid, actually sodium acetate, right? Remember when no, wait a minute, that's not right. That's only got one oxygen in it. So what would that look like? That would be start off with that, then that oxygen would be gone, and we would have like that, wouldn't we? That's the only thing that makes sense to me. And then the other molecule is let's see, it's only one hydrogen, I think. Yep. Like that. This one would have stronger intermolecular attractions than this one. So I would expect the melting point to be higher for the first one. Higher melting point, yes. This would be it's an aldehyde, ethaldehyde. We'll come to that later. I'm getting sidetracked. Okay, we've talked about hydrogen bonding before. We don't have to beat this horse anymore. You need nitrogen, oxygen, or fluorine attached to a hydrogen in order to have a hydrogen bond, to form a hydrogen bond. And the hydrogen bond forms between the hydrogen of one molecule and well, let's put it this way. A can be either nitrogen, oxygen, or fluorine. If we're talking about a pure substance, then these are the same molecules. And the donor, I see what they're doing. DO means donor. Hydrogen bond donor is the one that donates the hydrogen to the bonding. Okay. And the hydrogen bond acceptor is the one that accepts the bond with the hydrogen. So that A, if it's pure substance, the A and the DO are exactly the same. Right? So if we had something like this, let's see, H, F, then this F, right? This would be the donor, this would be the acceptor. And you would never get something like that because they're the same charge. All right. Do we need to beat? I don't think we need to beat this horse. You just need to recognize that it's always the hydrogen partially. It's not a complete covalent bond. It's a partial attraction. This is intermolecular attractions between the hydrogen and the acceptor from the other molecule. Now it could be there's several. Oh, I see what they're doing. We've got several possibilities here. If you've got ethanol in that far left one, ethanol, then the hydrogen from one is going to donate to the oxygen of the other. That's the only possibility. But if you have a carboxylic acid, then the hydrogen can, and most likely will bond with the oxygen of another molecule, but it can also donate to the carbonyl group, carbonyl oxygen of the other one, simply because the hydrogen is slightly positive and the carbonyl oxygen has excess electrons in those lone pairs. Plus, it's drawing electron density away from the carbon, just like the OH is. Okay, so you have two possibilities with a carboxylic acid. And I think the point here is that hydrogen bonding with the alcohol is overall going to be weaker and give you a lower boiling point than the acids, because you have these other possibilities for attractions. Does that make any sense? Okay. Think so? Okay. We just talked about that. The extent of hydrogen bonding increases as the total number of potential hydrogen bond donors and acceptors increases. Okay, that's what we just said. Here we go. Strength of the hydrogen bond. The strongest hydrogen bonding will be with hydrogen bonded to oxygen. And if you look at the periodic table, you see that the electronegativity of oxygen is going to be greater than nitrogen. It's to the right of nitrogen. So the polarity of the bond between nitrogen and hydrogen is less than it is between oxygen and hydrogen. That makes the strength of that attraction weaker for the nitrogen ethanamine versus the ethanol. So see, all we've done in there is substitute oxygen for nitrogen, or nitrogen for oxygen, to try to compare apples and apples. And the boiling point of ethanamine is much, much lower than it is for ethanol. Now, remember that number, 78 degrees, because when we distill ethanol out of our wine, right, that's the magic number. Did y'all do any distillations in your med technology? Didn't do any? Okay. Okay. This just says we can induce dipoles. For this propane molecule, it's nonpolar. But those electrons are not static. Those electrons are always on the move. And what that means is you can temporarily redistribute the electrons so that they're more dense in one place than the other. If that happens, then they can induce, because that middle one shows you that you're concentrating electrons on that central carbon. And what that does is it pushes electrons away from the carbons on that other molecule toward the other side. And when you do that, you temporarily have a slight positive and slight negative, and they attract. Now, this is London's explanation for how these molecules are able to bond. And we know that it happens, something happens. And this is London's explanation. Something like this must happen because gases become liquids and liquids become solids as you decrease the temperature. So nitrogen, the dinitrogen molecule, right? If this were not the case, then it would stay a gas all the way down to absolute zero. But when you reach minus 195 degrees C, it turns into a liquid because of this phenomenon. Okay. What we're trying to illustrate here is when you're looking at molecules, and not just the the number of carbons in the molecule. If we drew the homologous series for alkanes, right? And we went from, we went from methane to ethane to propane to butane and just kept going on down. Right, we go on down to octane in your gas tank. And then we go on down to, let's see, about I think 14 maybe might be diesel. Actually, it starts at 12, but illustrate the point. 30. And you just keep going on down. You go down to asphalt. This homologous series says that as you increase the mass of the molecule, the molar mass of the molecule, you increase the melting point. So you get down here for asphalt, they're solid. Down here, they're really kind of a honey-like. Diesel is thicker. And then, of course, gasoline flows fairly well. And then you get up here and you've got gases. So as the length of the molecule increases, you have more opportunities for those London dispersion forces to come into play. There are other things involved, especially when you get really long molecules like entanglement, but that's beside the point. Then when you get branching, what branching does is it destroys the ability for these long molecules to associate with one another at multiple points. So when you branch it, now you've got this big blob instead of this long chain that can lay side by side with other chains. So when you branch, then dimethyl propane, 1, 2, 3, 4, 5 carbons. So let's compare that to pentane, the one below it. The melting point for dimethyl, let's see. Now, did it just destroy my argument? Yes, it did. Dimethyl propane. Well, let's see. 1, 2, 3. We can look at it two different ways. Total number of carbons or a branched propane. So if we look at propane, the melting point is minus 188. Whereas the melting point for dimethyl propane, because it has those two extra groups, is a much higher temperature. But if we go to dimethyl propane and pentane, which is the same number of carbons, pentane has a lower melting point, but a higher boiling point. I can't explain that one. Sorry. It's just, if I were a trained organic chemist, I could probably rattle it off. But not. If it were important, then I would figure it out. Okay. So we're trying to make sense of it here. Induced dipole interactions tend to increase in strength as the contact surface area increases. Okay. So we went from pentane to dimethyl propane. Well, maybe it is working. Yeah. Boiling point. Well, if we focus on boiling point, not melting point, boiling point would be higher for pentane because the surface contact is greater. Okay, so that works. I'll take it. Stop me if you have questions. Okay. Oops, too far. Come on. There. Solubility. All right, we mentioned already, like dissolves like. And this is largely due to polarity factors. We're going to have, if we try to combine pure hexane with pure water, we've got pure hexane is nonpolar, pure water is hydrogen bond, the strongest polarity you can get. They do not combine. You will get a separation, right? You try to put them together, the hexane will float to the top because it's less dense. We're gonna, if I can get it worked out, what I want to do is, let's see. Oh, no, that's not this. That must be for second semester. So that's not an issue. I was gonna, for the second semester, I've got a lab where we do phase extraction, biphasic separation, where you extract in a mixture of acetone, water, and hexane. And then once you get the extract out of the material, you add more hexane to it, and it causes the two layers to separate. And the nonpolar goes into the upper section. The polar stuff stays in the bottom one. And then you're seeing a separatory funnel. Excuse me. It's got a big bulb at the top and a stopcock down here. With a plug at the top. And you get two layers. You just drain that layer off and keep it or throw it away, it doesn't matter. And then drain this off and do something with it. Okay. Oh, I'm using up too much time. Water and ethanol will mix because of the ability to hydrogen bond. Excuse me. Okay. If we want to qualitatively or semi-quantitatively arrange the strength of attractions, the least attractions will be between nonpolar. The strongest will be between ion, and then intermediate will be ion polar. This term solvation, I think we encountered that one in general chemistry when we were trying to calculate the difference in strength of attraction between water molecule and these two comparable compounds. And we used terms like heats of solution and other things to calculate this strength of attraction, this solvation. The process itself simply means that when you put a compound into a solvent, and our example here is going to be water, what happens is the molecule is surrounded as much as possible to the maximum extent possible physically without steric hindrance, is surrounded by water molecules. So the sodium is going to be attracted to the oxygen side of the water molecule, and this methanoic acid or formic acid is going to be attracted to the positive side of the water molecule. Now, it doesn't stop there, right? Because there are billions and billions of water molecules out there that may not be directly attracted to these molecules, but they still exert an attraction on the water molecules because they still have those hydrogen bonds formed with those molecules, and they're pulling. And the end result in this sodium formate compound is that sodium is separated from the formate ion by this process of solvation. So where this is leading is, if you have a reaction that you're studying where you're interested in the reaction of formate, recognize that the sodium is a spectator because it's solvated out here and the formate is over here. Okay, in which solvent would you expect sodium chloride to become more soluble? Diethyl ether or propanol? I think we can do that one without even going through the process. Which one is more polar? The one with the carbonyl on the end of the molecule. The oxygen in the middle of the molecule may show slight polarity due to its geometry, but it's not nearly as strong as that oxygen hanging out here with its two lone pairs sticking out in space. So sodium chloride should be more soluble in propanol. It has a larger dipole. Okay. What we're trying to show here, this is sucrose. It's a disaccharide. If you took biochemistry, you'd get a snootful of this one. We're bonding glucose on the left, right? It's a 6-membered ring. Fructose on the right is a 5-membered ring, and they're bound in the middle through what's called a glycosidic bond. What we want you to focus on is the solubility of sucrose. If you try to dissolve table sugar in water, you can go past 50-50, way past, right? You can put so much sugar in there that it's more sugar, a lot more sugar than it is water. And the reason for that is all of those OHs sticking out the sides. Hydrogen bonds, right? You can form numerous hydrogen bonds, and solvation is astronomical with these molecules. The OH groups are hydrophilic, and the R groups, which are not very prominent, are hydrophobic. Okay. The more soluble, the higher, let's see, let me use their terminology. If we have, in this homologous series, we have alcohols, right, going from 1, 2, 3, and 4 carbons. And they're normal alcohols. That's the old terminology. If the OH group is on the end of the chain, we call it normal. But IUPAC says 1-all, right? It's at the end, on the end of the molecule. So if we compare each one of these and their solubilities, we find that the higher the ratio of the total number of carbons to the hydrophilic functional group, the higher that ratio, the more carbons you have for the individual functional groups, the less soluble. Because you're generating part of the molecule that's away from the OH is hydrophobic. Right? It doesn't want to be in water. But the hydroxyl drags it into the water solution up to a certain point. And the more carbons you have out in that chain, the less soluble. Okay. Would you expect each of the following compounds to be soluble in water or insoluble? Well, yeah. A ought to be very soluble, right? It's got 2 hydroxyls. And the ratio is like 1, 2, 3, 4, 5, 6 carbons. 6 to 2 hydroxyls would be a 3-to-1 ratio. Whereas B is 6-to-1 ratio, so it's less soluble. And then C is, how many are in 2-naphthol? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10-to-1. No, 11. 1, 2, 3, 4. Yeah, 10-to-1. So it went from 3-to-1 to 6-to-1 to 10-to-1. using that rule of thumb itself, we should say that the solubility decreases from left to right. Oh, 3-to-1 cutoff. I missed that. Yeah. Number of carbon atoms to the number of hydrogens group is less than 3-to-1. Okay. That's another rule of thumb. If it's 3-to-1 or less, the molecule should be soluble in water. And then we consider it insoluble or limited solubility if it's greater than 3-to-1. So B and C would tend to be insoluble in water. That's cyclohexanol is the middle one. Okay. Rank the boiling points and solubilities of these similar compounds. All right. We got a bunch of them. So what do we do first? The first thing you do, and this is to illustrate the sequence of decisions. What's the most important intermolecular interaction in each pure compound and group? Okay, the most important one is hydrogen bonding. That's the strongest. So we would put B and E together. They would probably be the strongest intermolecular attractions. Then we would take the ones with halogens, which would tend to draw electron density toward the halogen and make it look slightly negative, and put the C and the G together. Then we would take A, D, and F and put those in a group. So that would be our first division. Okay. And then within each group, we decide which would be the strongest attraction, and then assign relative boiling points to the overall order. Okay, so there we have our, actually, we're going to take, at first we put the chlorine together with the chlorine, but we know that the chlorines are opposite one another, so they're going to cancel out their polarities. So it's going to be with the other nonpolar groups. Then let's see, we call that arrangement ortho. Those two chlorines in the middle are ortho to one another. We'll talk about that later. I hope we do. I don't know. It may be second semester. And then the two on the end are the strongest. Then we want to subdivide each one of those. Right? Isn't that where we're going with this? Yeah. We find that we have these carbons sticking out here, and they tend to increase the boiling point. Right? Because you have an additional induced dipole ability by those extra carbons, those methyl groups sticking out there. So this benzene is going to be the lowest boiling point. And then with only one methyl group, the A is going to be the next. And then the dimethylbenzene is going to be the next. And then we find that we've already positioned this one in its place. Then we have the dichloro, the second dichlorobenzene, and then we have the hydrogen bonding ones. We've got more hydrogen bonding available on the very last one, so it's going to be the highest boiling point. Okay, rank these compounds from lowest solubility in hexane to highest solubility. All right, lowest solubility is going to be the most polar molecule, right? So the most polar molecule is going to be C. It's got two hydroxyls on there. So that's going to be the lowest solubility. Rank it from lowest to highest. So lowest is going to be C first. C is going to be the lowest. Let's say the highest solubility is going to be D. Now we just need to position the rest of them. All right. Yep. A B. Yep. I would say B. How about E? And then what do we got left? That's 4. A is the only one that's left. Yeah. So we're saying that CBEAD. CBEAD. Congratulations. Now, here's a concept that every organic chemist knows. In an environment where you're proposing a chemical reaction, the solvent can participate. It may not participate, but that's one consideration you always have to add to your calculus is, can the solvent participate in the reaction I'm proposing? If you don't want it to, then you want to pick your solvent to be neutral in this environment. So that's where non-protic or aprotic solvents come in. Protic solvents are those that can release a proton. They can do a proton transfer of some kind. Water is a good candidate for that. DMSO, which stands for dimethyl sulfoxide, is a non-protic solvent. Of course, sodium chloride is more soluble in water because it's polar, but DMSO may be slightly polar. Well, actually, it's more polar in water. How about that? I didn't realize that. Dimethyl sulfoxide. Yeah, dimethyl. No, that's sulfur, I think. Sulfoxide. I think that's dimethyl sulfoxide. Okay, so this sulfur is drawing electron density away from the carbons. Oxygen is taking them even further because it's more electronegative. Okay. Yeah, and it's trigonal planar. So it's an unbalanced geometry. All right. So the question is, in my mind, is if it's more polar, if DMSO has a greater dipole moment than water, why then is sodium and chlorine, why are sodium and chlorine more solvated, higher solubility in water than in DMSO? Okay. What we have here is steric hindrance. DMSO, let's see, did I draw that right? I think I did. DMSO is a huge molecule. You can't get as many of them around the sodium and the chlorine as you can with water. And that multiplier for water gives you a stronger pull. You can draw more of them into solution than you can with DMSO, even though DMSO has a higher dipole moment. Bulkiness of the methyl group. Yeah, those methyl groups are huge by comparison. Okay. So these are protic solvents, right? Water, ethanol, and acetic acid on the left-hand side. And aprotic solvents, typically those that can be used are dimethyl sulfoxide, yep. Propanone, acetone. Propanone is the proper name. Acetone is going to be printed on the bottle for your nail polish, remember. Doesn't produce any protons, and N,N-dimethylformamide, which is a mouthful. But you don't see any acidic hydrogens there. Now, there's one possibility on that N,N-dimethyl DMF, is that hydrogen on that carbon. I mean, is the that carbon is slightly positive. Okay. The carbon there you see is slightly positive. If you want hydrogen to be released for a protic solvent, then that hydrogen itself has to be positive. But the carbon's already positive. So it's not going to draw any more electrons. It's not going to make the hydrogen more positive. So that hydrogen on the next to the carbonyl is not acidic enough to be considered a protic solvent. And they probably discovered that by comparing chemical reactions. That'd be my guess. They knew that before they had the theory to describe why it was that way. Okay, I think we're getting close to the end of this, aren't we? Remember last week we talked about, didn't we talk about lipids? Right. We had 4 basic types of compounds in biochemistry. You have carbohydrates, like simple sugars and starches and cellulose. Proteins, fatty proteins, amino acids are polymerized in proteins. Then we have nucleic acids, right, that form the basis of predominantly the information carrying part of our cells. And then lipids. And the lipids I've described as operationally defined. A lipid from a natural source, it's a biomolecule that is hydrophobic, nonpolar. So then after that, we can go in and define, chemically speaking, structurally speaking, what these are composed of. Right? True fats. True fats, if you've had anatomy and physiology, you know a true fat is a triglyceride of glycerol. Right? You get this 3-carbon chain, and then you form, let's see, put your fatty acid out here. See, like this, and like this, and I think it's about like that. That's it, yeah. So you get 3 of these guys. And then you have whatever the chain for the fatty acid. And then we have 1, 2, a 2 there, 1 here, and 2 here. That's your triglyceride. And this represents a true fat. Oils also fall into this. The difference between well, an oil is a type of fat that has a low melting point. Like oil is liquid at room temperature, but it's the same chemical structure. Phospholipids, they generally have a phosphate group attached to them. Right? If you have, let's start with phosphoric acid. That's the best place to start. Right. Phosphoric acid. So this molecule is going to have 4 oxygens and 3 hydrogens. That means this one is going to be a double bond. Right? So the phosphate is generally attached at one of these oxygens. Right? There's your bond. Just add that phosphate to the lipid, whatever the lipid happens to be. It could be one of these, could be a different one. Then you get a phospholipid. And in biochemistry, phosphating a molecule usually does one of two things. It activates it for a subsequent reaction, or it stores energy. Like ATP, adenosine triphosphate, is an energy carrying molecule. So when one it's got three phosphates on it. If one of them is lead, now you have ADP and one free phosphate and energy. And that's a energy carrying currency in the cell. Steroids, they have a fused ring structure that I don't have memorized. And we'll see a picture of it in a minute. Waxes are kind of like true fats, only they're this part. And what you get is an alcohol combined with a carboxylic acid. So you dehydrate it, you take away this and that. That's water. And then you form that bond here. So you get this alcohol with an ester linkage to a carboxylic acid, and that forms a wax. And they're usually very long molecules because waxes are typically solid at room temperature. And that's what bees use to make their combs. It's these waxes. Okay. They generally are used to store energy, fats and oils to store energy in plants and animals, right here. And it's under control of physical activity, age, which means usually cellular activity decreases as you get older. So your body tends to store more of that. Right? You don't slow down your eating, right? But you do increase your fat storage. For men, I think it's related to testosterone levels. So I remember when I was in my teens and 20s, I could eat and eat and eat and eat all day long and never gain a pound. Okay, fatty acids go into making up this true fat, this triglycerol. Now, sometimes you can substitute something down here, either one or two. I don't know if any of them do three, but you can substitute something here rather than the fatty acid and modify the physical and chemical characteristics of that molecule. But it's based upon these fatty acids. And biochemists understand what these names mean. Linolenic, linoleic acid, oleic acid, all these are accepted names. We used, let's see, did we do, yeah, we did second semester. It was our first lab. We did the molar mass of benzoic acid by freezing point depression. Yeah. And we used lauric acid, I think, as a solvent. That was that first one. And then benzoic acid is benzene with a carboxylic acid group on the side. Okay, so I didn't have to go to all that trouble. There it is right there. This is how triglycerides or triacyl glycerols. The acyl group is the actually, it describes the bond itself. I want to call it an ester, but they're saying it's acyl, and that's fine. You know, 6 of one, half a dozen. Phospholipids. By and large, the phospholipid is created by forming this, substituting a phosphate for one of these fatty acids. That's not the only kind that can happen, but it's a very large part. And very often what it does is it forms a bridge linkage between this molecule and something else. So that's what they're trying to show you there with phosphatidylcholine. Is once you form the phospholipid, then you can attach choline on one side. And you notice what's happening here is we're changing the polarity of the molecule. Because with these bonds, we do have some polarity in here, but when you put a phosphate on the end of it, you've radically increased its polarity. And what that does is it makes this side of that molecule very polar and this side non-polar. So think, do you know what a soap is? Right. It's a saponified fat. You take sodium hydroxide, you'll break these bonds, and you form glycerol, reform glycerol, plus the sodium salt of that acid. And that allows the soap to do two things. This end dissolves in the oils that soil your clothes. You know, you're sweating and oils and water comes out, but it evaporates, so it leaves behind the oils in your clothes. This part dissolves in the oil. This side dissolves in water. And that allows you to wash things away. Now, the only problem is with soap, once you get these separate acids, they will attach to any ion, any cation you have. If it's sodium, great. If you've got sodium water, if you've got sodium in your water, then it works fine. But if you've got calcium and magnesium in your water, you got scum. Because one of these attaches to one, so calcium is a 2+ ion. You got this one on this side, you got another one on this side attached to that same calcium, and it just settles out as scum in rings in your tub. So we use water softeners, right? We exchange sodium for the calciums, and that softens your water. You'll notice also, if you wash your hair in the shower with hard water, it comes out kind of squeaky, right? If you live in New Orleans or Baton Rouge, and they've got sodium water down there, soft water, you come out and you try to dry yourself off, you feel like you can't get dry. Okay. So what these phospholipids do, among other things, is they help construct the cell membrane. So you got a bilayer. A lipid bilayer is the base structure for the cell membrane. And you have these long tails pointing toward each other, right? They're hydrophobic, so they stay away from water that's dominant outside and inside the cell. And then the water, the hydrophilic part of the molecule points out. And this, you can put these in solution and they are self-forming, right? They usually don't form continuous layers. They usually form what's called a micelle. A micelle is like a sphere, and you have the tails pointing in, and then you have the hydrophilics out here with water. We used to use that to form microencapsulated fish diets. You could put these types of molecules in your aqueous solution, and then you could put the substance you wanted to encapsulate, which was hydrophobic, and it would associate within this, and it was surrounded. And then when you dry it down, you've got this kind of a powder with your encapsulated material inside. And it's readily soluble, right? Because these are hydrophilic, right? You can just throw it in the water and Bob's your uncle. Okay, the actual membrane of a cell is much, much more complex. You've got channels controlling movement of things into and out of the cell. You've got things attached to the outside of the cell. that can elicit immune responses. It depends on the specialty of the cell. Steroids. Here's the base molecule for a steroid. This is called a fused ring. When you have a ring that shares two carbons between the two rings, those rings are said to be fused. So A and B shares two carbons, B and C, two carbons, C and D, two carbons. So you have these three six-membered rings and then one five-membered ring. And that's the core of steroids. And just the functional groups and the number of double bonds in here, and even aromatic parts to the ring, will determine what type of steroid it is. Could be cholesterol, right? Could be testosterone or estrogen. It could be a corticosteroid that's not naturally found in your body, right? That the doctor injects into your joints to calm the inflammation. Cortisone. Here's an interesting fact. Where does estrogen come from? Oh, no, I mean chemically. It comes from testosterone. You get testosterone first, and then it's converted into estrogen. Okay, so here are different examples. And we see cholesterol has that one double bond, and then it has that one attached on the five-membered ring out there. So that's cholesterol. And there can be different cholesterols. We haven't talked about isomers yet, right? But this is a generalized type of cholesterol. You can have different cholesterols. Testosterone on the top still only has one double bond with the carbons, but the double bond is moved. And you also have a carbonyl group and hydroxyl group and some methyl groups attached. Estrone, a type of estrogen. Okay, yeah, they're different estrogens. I should know that. Aldosterone is a hormone. It's you know what hormones do. They're small amounts of molecules that go throughout the body and affect biochemical reactions. And cortisone. All right. Okay, here's our wax. So you can see this ester linkage right here. It was a carboxylic acid, and then it connected with an alcohol. Oh, earwax. I forgot about that one.